Today we're going to be looking into section 2.2. This should be relatively brief, and we'll have a worksheet for Friday that involves this section as well as 2.1, which is what I went over in class on Wednesday. Anyway, this section involves itself with the absolute value function. So there's a couple of ways to think of this. I personally just like to think of it as a process. If you give me a negative number, I just take away the minus sign. If you give me a positive number, then I don't do anything. So you can verbally describe the absolute value function. I want to point out to you that there's another way to do it, which they're writing right in there in the book. The absolute value of x is the square root of x squared. Let me copy that onto this little sheet of paper. Absolute x is the same thing as square root of x squared. Why is that? Well, if you have a number, whether it's positive or negative, when you square it, you're going to end up with something positive. So x squared is always a positive number. It could be 0, but it's 0 or higher. And then when you take the square root of that, if you look at the graph of the square root function, what's it look like? It's one branch of a parabola on its side. So the x squared that we're feeding into this thing is a positive number. That means we're over here, which is necessary because this graph won't do anything for you if x is negative. It doesn't have it doesn't give an output in that situation. So square root of x squared, well, it'll be defined because x squared being 0 or larger means that you're in the domain of the square root. But I think the more important thing is that square rooting and squaring are inverse functions. So what do you get if you square something and then you square root it? It's not quite true to say that you get the x itself. Why? Because like if I have, I don't know, say 3 in here, I square that, I get 9. I take the square root of 9 and I get 3 again. Yeah. But wouldn't I get the same answer from this process if I put in negative 3? Sure, negative 3 squared gets you 9. Square root that, you get back to 3. So this is really what's going on if you have a square and then you take the square root of it. You get the absolute value of x. Most often, when you're learning algebra, they tell you to always throw in a plus or minus when you're square rooting. This is why. So in fact, it's better if you have to take the square root of something to get an answer. It's better if you just treat that as an absolute value. Well, having said that, if we're going to treat things as absolute values, we need to know how to handle absolute value functions properly and be able to do various things with them. Well, look, this is not the only way to view the absolute value function. Probably the nicest way to think of it is this. The absolute value function is defined piecewise. There's two possibilities. If x is negative, you do one thing. If x is positive, you do another. And this will look a little backwards, but if what the x that I've just written down there, that's what you do when x is greater than or equal to 0. This thing, the negative of x, is what you do when x is negative. But it's supposed to be absolute values, right? So it's supposed to give you a positive number. Having that minus sign there, that looks weird. Like it's saying, oh no, give me a negative number. The point is, though, that we only use that negative x, that formula for the absolute value, when x itself is negative. So you're getting two minuses and they cancel. Okay, so, well, actually, that same definition is written right here in the book in a gray square. I noticed, unfortunately, I wrote them backwards the way they did. They mentioned the case where x is greater than or equals to 0 on the bottom, and then the one where x is negative up above. I did it in reverse, but the order that you mentioned the the parts of a piecewise function that's immaterial. All right, we're going to look at this other gray box on what page am I on? The first page of this section a little bit more carefully. The first thing says it's called the product rule. I'm worried about that because there's another thing that's known as the product rule that you learn in calculus, and so I'm not sure if that's a good idea to be naming this thing the product rule. Anyway, it is a rule that you use when you have products inside of an absolute value. And what it's saying is, if you're multiplying two things and then taking the absolute value, you'll get the same result if you take the absolute values first and then multiply those. I think that makes sense. Let's just think about this in terms of A and B, whether they're positive or negative. One thing I hope is clear. If A and B are both positive, that makes perfect sense. If A and B are both positive, then the absolute value of AB is AB. And absolute A and times absolute B, that's A times B. So both sides of that are the same thing, A times B. Equally well, if they're both negative, we get a good result because what happens to their product? It becomes positive. So the left side there is just AB. Well, it's the absolute value of A times the absolute value of B. It's the positive versions of A and B multiplied together. But that's exactly what the right-hand side is saying too. So that leaves the case where one of them's positive and one of them's negative. Well, notice that if that's the case, the product AB will be a negative number. But when we take its absolute value, it just gets rid of the negative sign. What does the product of A times the product of B do? I'm sorry, the absolute value of A times the absolute value of B do. Whichever one was negative, it's in the absolute values, so it turns it positive. So anyway, you should play with that rule a little bit and make sure that you buy it, because I'm really stating it here without proof. But it basically looks like you can kind of distribute the absolute values, right? If you have the absolute value over a product, just put it on each part. If you're allowed to do that, if I say the absolute value of A times the absolute value of A, well, that should be the absolute value of A times, I think I just said that wrong. If I did this, absolute value of A times A, according to the rule we just wrote, that should be the absolute value of A times the absolute value of A. Now, what I just did there is a special case of the rule we're seeing next. They're calling the power rule. This is absolute value of A squared being the absolute value of A squared. Well, and if I can do it for squaring, I can do it for cubing. Just throw one more factor of A in there, and so on. So that is, I'm attempting to argue for why this is true in general, that any power applied to A and then stuck inside absolute values, it's the same thing to take the absolute value and then apply that power. Why do they say this whenever A to the n is defined? Well, one reason is this: n could be a negative number. So it really means 1 over a power. And in that case, when A is 0, it won't be defined. It'll be dividing by 0 then. So that's actually one of the easier things to overlook when you're looking for when functions are defined and figuring out their domains. Negative exponents are just like reciprocal powers. So you have to realize you've got the potential for getting a division by 0 error when you see a negative exponent. The quotient rule, I would say that in combination with the power rule, the product rule and the power rule together basically hand you the quotient rule. But it's worth being able to deal with this. If you have a fraction inside absolute values, you can just kind of pop the absolute values out onto the parts of the fraction. And of course, neither of these things will be defined if b is 0. So I put a little proviso in there that b has to be not equal to 0. So I think all three of those rules are pretty obvious. And anyway, they're things we need to use in order to solve absolute value problems. These last two things, they're handy. Last three things, really, but well, one of them is kind of a non-thing. Anyway, when is the absolute value of something equal to zero? The only way that happens is if the thing itself is zero. That's I just said in words what that's saying in terms of equations. Absolute x equals zero if and only if, meaning this is the only situation in which it happens, x is equal to zero. If you are trying to solve an absolute value problem, you'll need this rule, that if the absolute value of some quantity, and it needn't just be the variable x, it might be some complicated expression in there, but the absolute value of that thing is equal to some positive number, and I said up front, or it says up front that c is positive. Well, that happens in two situations, and two situations only. Either the thing inside the absolute values is literally equal to c, or its negative is equal to c. You could say this, you could put kind of a different emphasis on that. X is equal to c, or x is equal to negative c. It's kind of just changing which one you think of as the one that needs to have its sign changed. And lastly, you're not going to get a solution of the absolute value of x being some negative number. That's what that last thing is saying. If c is a negative number, absolute value of x has no solutions. Let's just take a quick look at what those rules look like if we do things graphically. So here's a Desmos graph. First, let's just graph the absolute value of x. Cool. This is I hope that's not a surprise to you that you get this V-shaped graph. Let me turn the projector mode on. If I'm saying the absolute value of x equals 0, what I'm saying is the y-coordinate on this graph is equal to 0. Y equals 0 is that horizontal line that's in blue now, in other words, it's the x-axis. Is there a point on the absolute value graph that has the y-coordinate equal to 0? Yes. But it's just that spot right there at the bottom of the V. So, yeah, to get the output b to 0, the input has to be 0. Let's change this from 0 to a constant. And we're supposed to get a slider for k. Desmos isn't recognizing it when now I can add a slider for it. Okay, fine. I did it that way, and now I'll get rid of that. I just did trickery to get it to give me a slider. So the rule when k is a positive number, or I guess in the book it used c. I'm sorry. For me, constants are always k. I messed that up. Anyway, when the constant is a positive thing, saying the absolute value is equal to that constant, that has two solutions. One of them, when x is equal to the negative of that constant, and one of them, when x is equal to the positive of that constant. I could probably even plot those points. Let's see, it would be k and 0. That's the 1 point. See how that's directly under the intersection here? And the other point. Is it okay to write a second point in here? Yeah, it is. Oh, that's fun. So now I've got two green points. And if I change the slider, those guys go in and out. One of them's positive, one of them's negative. Right? That's kind of how you deal with absolute values. Okay. I thought it would be nice to see these in action, and example 2.2.1 here puts them in action. Let's go through some of those. I don't think we want to go through every one of them, but using these rules. Let's take the first one. 3x minus 1 in absolute values equals 6. Can we solve that? Actually, I think the example asks us to do more than just that. Is it enough? Yeah, it's enough to just do that. So absolute value of 3x minus 1 equals 6. There's basically two answers to this. Either 3x minus 1 is equal to 6, or 3x minus 1 is equal to negative 6. That's what the 2 points on either side of the absolute value sign said. But the only problem here is that, I don't have just x inside the absolute values. I've got 3x minus 1. But these two solutions are easy enough to find because that's the sort of algebra we've done a million times. If you add 1 to both sides, you get 3x equals 7 out of that guy. And then just dividing by 3, x is 7/3. If you add 1 to both sides on that guy, you get 3x equals minus 5. And then divided by 3 is minus 5/3. Now, so you see that, actually you can see in the book, they got the same solutions I just said, 7/3 and minus 5/3. I want us to see that graphically as well. So here's back to the Desmos screen. What I want to graph now is not absolute value of x, but the absolute value of 3 times x. I guess I didn't need to type x a second time, minus 1. It's still a V-shaped graph, and we'll talk about this more. It's that absolute value graph, that V-shape, transformed in certain ways. And we want to set our k equal to 6. Can I do that with the slider? If I'm careful enough, there you go. K is equal to 6. So there's one solution, and there's the other. Now you can see them because when I mouse over them, it names the point. And that doesn't sound like what I said. What did I say? Negative 5/3. Well, if you plug that into a calculator, minus 5/3 is indeed this, although it's been rounded up. It's really negative 1.6 repeating forever. And what's the other solution? 7/3. 2 is 6/3, right? So 7/3 is 1/3 more than 2. 2.3 repeating forever. And you see how the y-coordinates of those points are both 6. So indeed, we did the right sort of thing algebraically. My personal advice is when you're dealing with absolute value graphs and or I shouldn't say graphs, problems involving absolute value, and you need to solve for the unknown, sure, do the algebra, but I often like to do what we just did here, check by going back and looking at the graph, because there can become some complexity with these absolute value things that it'll fool you. Okay. That's one of these problems. How about we jump to the end? Number 6. Absolute value of x minus 2 plus 1 is equal to x. I should have labeled what I was doing before. This is example 2.2.1, number 6 in that group. Now, absolute value of x minus 2 plus 1 equals x. Well, my advice, whenever you have absolute values involved, is get them alone. Get the thing involving absolute values by itself, and then you can use this rule about absolute value stuff. So in this case, it's just subtract 1 from both sides. Okay? So when do you get a solution to this? Well, you either have x minus 2 is equal to x minus 1. That's odd. Or x minus 2 is equal to the negative of x minus 1. Now, this first one is crazy, isn't it? No matter what x is, if x is the same number on both sides of the equation, and that's how x's work, you're never going to have 2 less than x be the same as 1 less than x. They're different values. But this other thing, maybe that could happen. So let's do some algebra on it. X minus 2 is equal to the negative of that. Well, just distribute the minus sign, so you get x minus 2 equals negative x plus 1. How about if we move the numbers to one side and the x's to the other side? So how about we'll do the numbers first. Add 2 to both sides. Then you'll have x is equal to minus x plus 3. Now add x to both sides, and you'll get that 2x's is equal to 3. And finally, I don't need to write this, just cross off that and divide by 2 on this side. X is 3 halves. So the one thing led to an impossibility, the other gave us x is 3 halves. There's a unique answer to that one. Let's again, verify that with a graphical method. So what was inside our absolute values in this case? Well, I'll stick with the original form. It had x minus 2 in absolute values, and then there was a plus 1 on the outside. Right. Let's not do this with the slider anymore. The other side of that graph was simply y equals x. Let's just call it x. Okay, so yeah, in red we have a V-shaped graph. In black, we got a line. Do they cross somewhere? Yeah, but it's really just at one point. And what is the x coordinate of that point? 1.5. Well, that's 3 halves. That's what we got at the bottom of the page there. Next, I want to go through the next example in the book, but I'm going to do this much more briefly. In fact, I'll just look at one of these, so you can see what the example is about. It asks us to come up with what do the graphs of these various functions involving absolute values look like. The reason I'm going to only do one of them and treat this very briefly is there's a better way than what I'm going to show you now. But using these tools that we've just played with, we can indeed, figure out the graphs of that. So let me just read to you what it says in the paragraph before. The strategy for graphing that they're going to use at this point, at least, is just use the definition a lot, and also use what we know about the graphing linear functions. That's fine, and piecewise defined functions. Both things that, linear functions, actually, I think everybody knows from before this class, and piecewise defined functions we did back in chapter 1. All right, so I'm going to concentrate on number 2 in here. The function g of x is absolute value of x minus 3. So whenever you're trying to graph something, one of the first things you should do is just say, hey, I need to get some points that are on this graph. I need to get some places to work with. Right? And one of those points is almost always really easy to calculate, because you can calculate the function applied to 0. What would g of 0 be here? Well, absolute value of 0 minus 3. That's really just a negative 3 inside the absolute value, so that's 3. And this means that when the x-coordinate is 0, the y-coordinate will be 3. In other words, the y-intercept is 3. Or probably I should say 0, 3. It's a point. Yeah. So now we've got a point on the graph. What else do we need? Well, often it's another point that's useful or interesting to know about is the other intercept, when x is 0. Wait, I just said that wrong. When y is 0. So how do we find the y-intercept? Well, since I'm working on this piece of paper, I should probably arrange for it to be able to see the whole thing. So let's find the y-intercept. I just did find the y-intercept. Let's find the x-intercepts. There might be more than one x-intercept. What does that mean? What does that mean to do? If you're talking about the x-intercepts, that's where y is equal to 0. Maybe that's why I sometimes confuse the two of them mentally. So that means that our function will be equal to 0 at those x values. In other words, we're going to solve what x values give us. Absolute value of x minus 3 equals 0. This is one of the rules we had. When is some absolute value of a thing equal to 0? Only under one circumstance. It's when that thing is equal to 0. So to do this, you simply go, okay, what's in absolute values, which is x minus 3, has to be equal to 0. Okay. Well, what does that say to you? X has to be equal to 3. So now I've got 2 points on the graph. This is when this is the point 3 comma 0. The other one was the point 0 comma 3. That's 0, 3. Here's 3, 0. So that's 2 points. Now, if this thing were a line, we'd be done. We would just draw the straight line through those 2 points. That's not quite the deal here. So let's think about the piecewise definition of absolute value, because we can use that with a slightly more complicated absolute value like this one. You see, g of x, the absolute value of that thing, well, it's equal to one of two things. It's equal to x minus 3 itself whenever x minus 3 is positive. And it's equal to the negative of x minus 3 whenever x minus 3 is negative. That's what that definition of absolute value says, just replacing the x's with x minus 3's. All right, so where do I go from there? Well, to say x minus 3 is greater than or equal to 0 is just the same thing as I would do add 3 to both sides of that inequality. So we have that g of x is x minus 3 provided that x is greater than or equal to 3. And well, we should simplify. The negative of x minus 3, the easiest way to take the negative of something that's a difference is just to flip the order, right? You've got x minus 3, the negative of that is do the operation the other way around, 3 minus x. And that's what we do when x is less than 3. Notice that here the dividing line was at 0, here the dividing line is at 3, but it's really those are equivalent. Okay, so what's the graph of x minus 3 look like? Because that's what we're supposed to graph when x is to the right of 3. That is, if we're over here, we're going to be graphing x minus 3. That has a slope of 1 and a y-intercept of minus 3, which means it's this graph. It's the y-axis down here at minus 3, has a slope of 1, right? But we're only going to draw that graph when x is greater than or equal to 3. Okay. So that's this part of it. And what does 3 minus x look like? Well, you can see the slope there is minus 1. It's a descending curve with a 45-degree angle. And the y-intercept is 3. That's this guy's point. And to go descending with a slope of minus 1, let's go like that. Now, that graph, the graph of 3 minus x continues on both ways. But again, we're dealing with that only when x is less than 3. So this bit of it is not there, just like this bit of the other graph wasn't there. So do you see how we got the V-shaped graph out of all that? That's a fine way to work your way through to getting the graph of a thing. And I mean, an even better way probably is to turn to some technology. Let's just let's do that quickly. Absolute value of x minus 3. We don't need that plus 1 on there. There it is. Y equals absolute value of x minus 3. It's just like I sketched it on on this other thing. A V-shaped graph with the bottom, that little pointy thing right at 3 on the x-axis. A little quicker to do it this way. What's a better way to think of this? What we've got is the absolute value graph, which is a V-shaped thing with its tip right here at the origin, shifted over 3 units. That is, smarter to, rather than going through all the rigmarole we just did, is think of this as shifting an absolute value graph horizontally by 3 units. If I turn that into a K, get a slider for K, start K at 0, yeah. So that's a horizontally shifted version of the absolute value graph with no shift. If I bumped K up to 3, we get the graph we were just talking about. I think, generally speaking, this is the better approach. Let me come back to one of these other graphs. This is example 2.2.2, part 4, number 4 in that. Whoops, I need to do this where you can see it. Yeah, so the function I of x, they just ran out of letters, so they're up into the high parts of the alphabet. I of x is 4. Okay, I didn't leave room for my equal sign. 4 minus, cursor's right on the thing, 2 times the absolute value of 3x plus 1. Now, I could just type all that into Desmos, but that wouldn't be quite as much fun as showing you this in an evolutionary way. Starting with just the absolute value graph, we'll slowly add parts of this transformations that modify it. All right, so y equals absolute x. That's our starting point. What's the first change that's made to x in here? It's that timesing by 3. So if you look at what's bound most closely to the variable, it's multiplication by 3. And what effect does multiplying x inside of the parentheses or inside of the absolute value braces do? It may look to you like this graph just got taller, but in fact what happened is it got squished horizontally. Visually it has the same effect, but an inside change is a horizontal change. So 3 times x looks like a more sharply pointed absolute value graph. The v is taller or squished in. What does adding 1 do to it on the inside of the function? It moved it. But watch out how much it moved it. Did it move it 1 unit? You can probably see that it didn't. This is not 1 unit away. Plus 1 should have been moved sideways 1 unit, but it didn't. It's only 1/3 of a unit. What's going on there? Well, if this didn't have the 3 on there, that's the standard guy moved 1 unit. Well, the multiplication by 3 has an effect. So the easiest way to work through this, why is it only shifted by 1/3, is to use that rule about when is the result of an absolute value calculation equal to 0. It's only 0 if the thing inside is 0. And when would 3x plus 1 be 0? Just, you can almost mentally solve for x in that. It's at negative 1/3. Next, there's a times 2 on the outside. Now we're finally into outside changes. So we had something that was tall, or it looked tall anyway, it was just scrunched in, but now it's been stretched vertically as well. It's even taller or even skinnier looking. But notice something else about this thing. It's not really times 2 that I want. It's times -2. What does that do to the graph? That's a vertical reflection. So -2 times absolute value of 3x plus 1 is what we're looking at now. And what if we bring in that 4? Yeah, okay. The 4 up front could have been a plus 4 on the end, too. So that's a vertical shift by 4 units. Yay. So we've got the graph of this thing by thinking about the transformations a little at a time, starting with the inside changes and ending up with the graph here. Now, the other approach might have led us to finding things like these intercepts more quickly. But locating where that vertical point is and locating the 2 intercepts. I said vertical point. That's a weird name for it. I always want to call it the vertex because it's like the vertex in parabolas, but it's not either. So anyway, the point. Let's call it the pointy part of the absolute value graph. We can locate that from just thinking about what the shifts are. 4 vertically, 1/3 to the left horizontally. And then if you know where that location is and you know the 2 intercepts, it's a matter of just drawing 2 straight lines from there. The last example that I want to run through with you about absolute value functions is this one, 2.2.4. It's just got 2 different absolute value functions. It's getting a little more complicated, or getting more interesting, in fact. This first one in number 1, it's the function f of x is defined as take the absolute value of x and then divide it by x. Now, I hope one thing about that is pretty obvious. If x already was a positive number, then you've got x over x. Yeah? So you're just going to get, what's x over x if x is positive? Well, a number divided by itself gives you 1. Yeah? So f of x apparently is equal to 1 when x is positive. What is it equal to if x is negative? Well, maybe I should say less than or equal to 0. Let me not do less than or equal to 0 because, if we had x equal to 0 in the bottom, we're dividing by 0. I guess it's 0 over 0 in that case, but still. So let's just do x actually less than 0. That's tough. I mean, it's still sort of 1, but not really, because excuse me. If x is a negative number, which is the case we're dealing with, then the one in the bottom is negative, but the thing upstairs is the negative of that negative. It's positive. Notice we'll have a positive absolute value of x divided by x, which is a negative number. You still get 1, but with a minus sign. Well, that's an intriguing graph. First of all, it's not defined at 0, but it's always 1 if you're to the right of 0, and it's always minus 1 if you're to the left of 0. This is known as the signum function, which is just Latin for sign. It's the function that tells you the sign of the number x. Signum. I like that name. I don't know. They never mentioned it in the book, so I thought I'd tell you that. What's its graph look like? Well, it's not too hard. We've got 2 cases. You get 1, provided that x is greater than 0. I'm worried that I'm not remembering how to do that notation. It might be a semicolon there. And minus 1 when x is less than 0. Yeah, apparently I've drawn it. I've put the notation in wrong. Yeah. Is it regular colon? Apparently not. Is it just a comma? Oh, heck. This is embarrassing. I've done this previously, so let me. Oh, I had to do this previously for something. So, oh, I'm sorry. I get it. I need to name the interval first, and then a colon, and then the formula. That's should have checked that before I got started recording this. All right. Can I just go new graph? Yeah. Okay. So it was supposed to be x is bigger than 0. In that situation, we're going to plot 1. And x is less than 0. In that situation, we're going to plot -1. That's what the graph looks like. Although this Desmos picture of the graph kind of has an issue, or I think it has an issue. It looks like it fails the vertical line test. You see how the y-axis would hit both of those red lines? And it doesn't fail the vertical line test because, in fact, it's not defined at x equals 0. So if I were drawing this by hand, I would plot the point 0, 1. Let me do some work on this. First, I want it to be the same color as the graph. And secondly, I want to use that open line style. And I should also plot the point 0, -1. And let me make those same changes. We want it to look like it's part of the same graph. And the open line style tells us that it's not part of the graph. So that's how you would in Desmos do this. Of course, if you're sketching it by hand, you wouldn't have to bother with all that. You just draw the 2 open circles and then the horizontal lines from there. I'm not sure that's worth doing. That's an interesting function. Really kind of a pain in the neck to draw if you want to do it from first principles, because the usual thing a person does if they want to draw a graph is figure out the intercepts. Does this thing have a y-intercept? Nope, it's not defined when x is 0. So it has no place that it hits the y-axis. Does it have an x-intercept? Nope. The values it has are either 1 or -1. It never hits y equals 0. So it has no intercepts, but it's actually not that hard to graph, even though it's uncomfortable there. G of x here is tougher. And my advice on this is not do what they do in the book, which is to analyze that through. I would turn to technology right away for something like that. You have 2 different places where the absolute values are used in this guy. So it's the difference of 2 different V-shaped graphs that are shifted by various amounts. And some funny business happens in that case. It's hard enough that it's probably not worth your while to do it. So just plug something like that into a calculator and see what it looks like. I honestly don't think it's worth your time to go through all the analysis that they do in the book. But if you're curious, the full solution is written out here under number 2 in that example. So go for it if you want to try to work your way through all that stuff. Okay, so that is all I needed to say. Oh, this is a picture of the graph of that function with the thing that involves 2 absolute values. It's sort of weird. You get constants for a lot of the time and a straight line. It's sort of amazing that a single formula could produce this graph. If I were told I had to create a graph like that, I would have gone with a piecewise function to do it. But it is possible to create something like that with a pair of different absolute values. Anyway, that's all for section 2.2. This will be getting posted rather late Wednesday evening, but I think it's still plenty of time for you to watch it before class on Friday. So see you then.